This is the first lesson in a lecture series introducing you to energy storage elements, specifically capacitors and inductors. To date, the elements that we have looked at, if you've been following either in the course or in the various playlists online, have been resistors as our classic passive element, independent voltage sources, independent current sources, dependent current sources, and dependent voltage sources. We've also introduced a couple nonlinear semiconductors. We introduced diodes and then MOSFET transistors. But of all of these, none of these elements actually store energy. I should be careful about claiming that because our voltage source, which is like a battery, certainly is able to deliver a net amount of energy. But when we think about the linear elements, recall that the elements that were linear were those that agreed with superposition, which meant that if you plotted, say, voltage versus current for a particular device, it had to be a straight line and it had to cross through the origin for it to be linear. So a resistor is a good example. A resistor would have a slope of R and it would cross through 0. However, a voltage source has a constant slope. It's a straight line, but it doesn't go through the origin. The current source, similarly, is a straight line, but it's vertical, so it doesn't go through the origin. Now, controlled current sources are going to be similar. They're, depending on what the controlling element is, they could either go through the origin, but they could also not go through the origin. And similarly for controlled voltage sources. So we can't say exactly for these. The diode, we know that a real diode is, well, highly nonlinear anyway, and it doesn't, yes, it does cross through the origin, I suppose, but it is certainly not a linear element, okay? And if we were to plot something for the MOSFET, we would see something like this. Oops, that would be I versus V across the device. So the main linear element that we have here is the resistor. And so within our linear elements, we don't have any linear element that stores energy. So I guess that's my point here is these elements can deliver net energy. Okay, so they store energy, but they are not linear elements. I know that's confusing to some because they would say, well, we solve linear circuits all the time with voltage sources and current sources, and you do. But the voltage sources and the current sources are considered stimulus to the linear networks, the circuits that remain without those independent sources. We call that a network. And it's the network that's linear, and we treat the voltage sources and current sources as inputs to our linear network, and we do also, all the linear tool tricks like superposition, etc. So what's unique now as we introduce capacitors is that we're going to find that we have two types of elements that are linear elements, okay, linear elements that can store energy. So capacitors and inductors are the first linear elements to store energy. So that's what's new. That is what's new about looking at capacitors and inductors. And I want to illustrate this graphically here in the following minutes. So let's consider the elements, or the symbols for a resistor, capacitor, and inductor. And then we will consider some waveforms across, or waveforms associated with each. So the resistor has a voltage VR, IR, resistance R. The capacitor has a capacitance C, a current IC, a voltage VC. And the inductor has an inductance L, a current IL, and a voltage VL. For each of these elements, there is a VI relationship, a constituent relationship that relates I and V. For the resistor, we have VR is proportional to IR. It is specifically VR is equal to R times IR. We can also then write IR is proportional to VR. For the capacitor, we have that the voltage is proportional to the integral of the current. Specifically, we have that the capacitor voltage is equal to 1 over C integral of the current. We can also write that the capacitor current is proportional to the time rate of change of capacitor voltage. If you take the derivative of both sides in this expression, you will arrive at that. And specifically then, we have that IC is actually equal to the capacitance of our capacitor times dVc dt. For the inductor, we have that the voltage is proportional to the time rate of change of current. Specifically, we have that the voltage of the inductor is equal to the inductance of the inductor times the time derivative of the inductor current. We can also write that the inductor current is proportional to the integral of the inductor voltage. Precisely, the inductor current is equal to 1 over the inductance times the integral of the inductor voltage. Now at this point, this probably seems quite abstract, or what does this mean? What's the significance of it? And so now we want to look at some waveforms that will highlight how an inductor and a capacitor behave differently from a resistor. So let's begin with the resistor, and let's say that we apply a square or bipolar pulse voltage to our resistors. So we're going to apply this in time. We'll apply 10 volts and minus 10 volts. And this is VR, and I will not always show the voltage or current as a function of time, but in all these graphs or plots, time is implied. Let's suppose that the resistance in question is 1 ohm. Then the response that we would have in terms of current is simply going to be VR over 1 ohm. And so we will have a current that will respond in the same manner, or have the same response in shape over time as the voltage. It'll be 10 amps and minus 10 amps, and then 0 at all the other times. Now what we'd like to do is consider the power that is being delivered to the resistor during this time. So power, little p in this case because it's a function of time, little p, we're looking at instantaneous power, is going to be equal to the voltage across the resistor times the current through the resistor. So we'll take a product of these waveforms. In this case, the product is going to have the same shape as both the voltage and the current. Oops, I take that back. Let's be a little careful here, mister. So when the voltage is at plus 10 volts and the current is at plus 10 amps, the product is 100 watts. When the voltage is at minus 10 volts, the current is at minus 10 amps, and the product of minus 10 times minus 10 is plus 100 watts. And if we let's assume that let's call this time 0, and let's call this time t period. Okay, so in other words, this last little bit here is the same as this first segment. This signal is going to keep repeating itself. So it looks like we have 1, 2, 3, 4. We have 4 segments to our period. So for 2 segments, we are at 0 amps, volts, and watts. And for 2 segments, we're at non-zero values. So over a period, which will consist of this distance from here to here, we have an average power. Okay, so if this was going to keep going, we'd end up doing this again. All right, so I'm interested in getting the average power. It looks like we deliver, on average, just graphically looking at this, we deliver 50 watts. 50 watts dissipated on average. So applying this bipolar pulsed 10 volt voltage to our resistor results, to our 1 ohm resistor results in an average of 50 watts being turned into heat. Now let's look at what happens when we apply either a pulsed voltage or a pulsed current to our capacitor and our inductor. We'll begin with applying this voltage to our let's see, we'll apply this voltage to our inductor, let's say. Okay, so we have, for our inductor, we will have a, let's see if I can draw this over here. I'm just going to repeat the same voltage waveform. Okay, so this is VL of t, still going to be 10 volts and minus 10 volts. And we're looking at this in time. Now, we need to compute or determine the current response. And we see that the current is equal to the integral of the voltage. The other way to look at this is, and so we can compute the integral. We can certainly do that. The other way we can look at it is we can also look at this expression here, where we see that the slope of the inductor current is, actually not that one, let's look at the exact equality there. The inductance times the slope of the, let me rewrite that one, let's do it this way, dIL dt. I'm going to solve for that and write it as VL over L. Alright, there we go. So here we see that if we're applying 10 volts, and let's assume that we have an inductance, we'll assume L equal to 1, and the units for inductance is Henry. Okay, although a Henry is very large, so we rarely, I've never worked with an actual 1 Henry inductor. Usually a large inductor is something on the order of millihenries, and we work with microhenries, even nanohenries. Here for ease we'll just assume 1 Henry. And so here what we find is that if we apply 10 volts and that's applied to a 1 Henry inductor, then the current is going to change at a rate of, and this is all SI units, so that means that the rate will be 10 amps per second. Okay, it's constant, it's positive, it's going up. So we can draw this current as going, current is going up during this time. If the voltage across the inductor is 0, then the slope is 0. So if it's 0 volts across an inductor, then the time rate of change of current will be 0. And so during this region here, it's not going to change. In the following segment where we apply a negative 10 volts, now di dt will be minus 10 volts over 1 Henry. And so it'll go back down at the same rate that it came up, because it's minus 10 like it was plus 10. And so this is the current that we have. Now notice that if we go back to our integral form, this one here, we could have solved for this current waveform as well if we just simply evaluated the integral. So 1 over L, 1 over 1 Henry, integral of 10 volts would just be 10 times time, right? And then integral of 0 volts would evaluate to 0, so we wouldn't accumulate anything more, and then integral of minus 10 volts would have a term of minus 10 times time. Now, this form of the inductor current, which is just with I guess indefinite form 1 over L integral of VL dt, we should be careful and say that we either would say this is integrated from, you know, minus infinite time up to some time t, and in which case I should probably make this, let's be mathematically correct here for a moment. So we'll use the variable of integration, we'll call it tau. It's still time, but it's the local variable for doing the integration. And we integrate from infinity past. We assume that infinity past there was no energy, there was nothing going on, up till present. That will give us, integrate that voltage over all of time up to the present time. That will lead to the value of the current at the present time. But a better form for this is to say, well, not a better form, but just a more practical form in our case, would be to say, let's start this off at some time 0, and then we'll do the integral of 1 over L from time t naught up to t. Okay, so the integral does not capture all of time past. This offset here, this constant, IL at time t0, captures all the history prior to time t0. The same will be true when we talk about the capacitor relationship here of the voltage of the capacitor being an integral, right here, and the capacitor voltage being the integral of 1 over capacitance times IC, though I won't write it at that point probably. So in other words, all that to say that we are not certain that when we start off this this inductor, we start looking at its current, that it's going to start from 0. It could be at some other current. So we really don't know what this is, but I'm going to assume that that this is 0, and I'm going to, we'll label this time here t naught equal to 0. Okay, so essentially we're going to assume that IL at t naught is equal to 0. Now, as long as there's no voltage applied, there's not going to be any change in current. But when there's the plus 10, the current will go up at a rate of 10 volts over 1 Henry. Okay, and that's going to be equal to 10 amps per second. And then it's going to plateau. Now, we didn't put any any time units, but let's say that this, we said we had four segments or sections in a period. Let's say this was actually 4 seconds. Okay, assume 4 seconds. So that would mean that each grid here is 1 second. So that will mean that we have actually reached 10 amps after applying 10 volts for 1 second. And notice that the voltage across the inductor goes to 0, but the current doesn't go back to 0. See, that's different than for the resistor. It stays at 10 amps. It only starts making its way back down to 0 amps when we apply negative voltage. And so here, when we apply negative 10, the slope will be minus 10 volts per 1 Henry, and that'll be minus 10 amps per second. And it will reach 0 volts after an additional second. Now's the real interesting part. Let's plot the power. So P of L of T. Now this is the power absorbed. Okay, passive sign convention. Power absorbed. So we take the product of the V and I. We'll have 0 up till until the inductor voltage goes to plus 10, and then it's going to be 10 volts times this rising current. So we'll get a a line, and what will it peak out at? Well, we have 10 amps. We have 10 amps here. We have 10 volts there, so that's going to be 100 watts. All right, 10 volts times 10 amps. But interestingly, as soon as we reach 10 amps, the voltage across the inductor is set back down to 0. And so, although we have 10 amps flowing, we have 0 volts across the inductor. So the power has to go back down to 0. So here we had 0 volts times 0 amps. Here we have 0 volts times 10 amps. Now, as soon as we apply a negative 10 volts, at the moment that we apply negative 10 volts, which is, right at this point here, for a brief moment we'll have minus 10 volts and minus 10 amps. No, I'm sorry, we'll have minus 10 volts and plus 10 amps, right? And so we'll have actually negative 100 watts. And now this will work its way back to 0 as we apply a constant minus 10 volts and the current is ramping back down from 10 amps back to 0. Okay? And if we look at the average power, okay, just like we looked at the average power over here, here we see something that's symmetric. It's centered about 0 watts, and it goes equally up to positive 100 watts as it goes to negative 100 watts, and the waveforms are symmetric. And so we can say that the average power, this is delivered, to L is 0. And this is fundamentally different than with the resistor. When the resistor has a voltage that goes back down to 0, there's no current flowing and there is no power being absorbed or delivered by the resistor. And whether you put positive voltage or negative voltage across the resistor, you're always delivering energy into the resistor, which is turned into heat. With the inductor, we can deliver energy into the inductor, and when the voltage goes back down to 0 in this region here, we still have a positive current. So we don't say that the current and the voltage are proportional like they are for the resistor. What we end up saying is that the voltage and the slope of the inductor current are proportional. So what this is demonstrating for the inductor is that the inductor is able to store energy. And you ask, well, where is it stored? Well, we have right here, if we take the area of that triangle, look at the peak is 100 watts and the duration is 1 second, right? Then we have 100 joules per second times 1 second, and then we have to do times 1/2 for the area of the triangle. And that gets us 50 joules stored. So after having applied a positive voltage and then returning the voltage to 0, if the voltage across this inductor remains at 0, so imagine we have an inductor and we just applied a voltage across it, but now we returned the voltage across it to 0, but we have 10 amps flowing around through it. And if this is 1 Henry, okay, the amount of energy that we have stored is 50 joules. there are 50 joules stored. In fact, the energy stored in the inductor is 1/2 inductance current squared. That's what we get. We get 50 joules. So there's energy that is stored from the initial applying of a positive voltage. And then we actually extract that energy when we apply a negative voltage. So if we were to consider what was happening to the voltage source when we apply negative 10 volts across the inductor using our voltage source, it would turn out that, and if we were computing the power being delivered to that voltage source, we would say in the first triangle wedge that I have colored here green, we are actually, or the source, the voltage source is delivering, let me do it this way, we'll use red in here. So we'll say the voltage source delivers 50 joules. And in the second pulse, there are 50 joules that are returned to the voltage source. And in between, those 50 joules are being held in the inductor. Where are they being held? We'd have to get into the physics a little bit, but the energy is being stored in the magnetic field of the inductor. Much like we'll see the energy gets stored in the electric field of a capacitor. The key, though, is to recognize that energy stored in an inductor takes the form of a current. So you cannot have any energy stored in the inductor if there's no current flowing through the inductor. You don't need voltage across the inductor to store energy, but you need current. And this will be the opposite for the capacitor. And we'll look at the capacitor now. So let me make a little room here. See if we can fit this in. Okay, for the capacitor, instead of applying a voltage, a pulsed voltage across the capacitor, like we did for the inductor, it's going to work out more appropriately if we apply a pulsed current. Okay, so we're going to apply a pulsed current. So this is going to be IC of t. It'll be 10 amps and minus 10 amps. And again, we have 0, 1, 2, 3, and 4. And these will be seconds. And we're going to assume, let's assume that we have a capacitance of 1 farad. Okay, F is for farad. Like the inductor, Henry, 1 farad is a very large capacitor. There are what's called supercapacitors that do have capacitances that are on the order of farad or multiple farads. Very low voltage capacitors that are only a couple volts, usually less than 3 volts. And so by and large capacitors that we'll deal with are anywhere from down in the picofarad, so that would be 10 to the minus 12 farads, all the way up to maybe millifarads, so thousands and tens of thousands of microfarads. But common values are in the microfarad, nanofarad, so that kind of puts a range on it. But for this example, we're going to use the 1 farad capacitor to keep things simple. So now we're going to apply this pulse, and we want to look at the current response. I'm going to look at this. Oh, here we have it right here actually already. We're going to find the voltage, and we can find the voltage in two ways. We could actually look evaluate the integral. There we see here that the capacitor voltage is 1 over the capacitance integral of the current, and that's like the case for the inductor. This really is, if I make this a definite integral, I would say it's going to be the capacitor voltage at some time t0 plus 1 over c integral from t0 up to the current time capacitor current. Okay. What I'd rather use here is to look at this expression here, which tells me that the I can rewrite this as the slope of the capacitor voltage is equal to the capacitor current divided by C. And because I mean, we have the current, we know the capacitance, we can calculate that slope. And just like in the case of the inductor, because there could be this initial constant, we're not necessarily going to have a capacitor voltage that's starting at 0, but we're going to, in this case, we will claim that it does. We'll specify it that way. So what we'll have here, we'll say VC at time t0 is going to be equal to 0 volts. We'll just define it to be that way. But it could, we could start off at 1 volt or some other voltage. All right, so for the first segment here, I've drawn it flat because the current is 0, and according to this relationship here, if the current is 0, the slope of the capacitor voltage is 0. And now when we go to plus 10, we're going to have a slope of 10 amps over 1 farad, which will be 10 volts per second. So it actually is going to go up, and we'll draw this slope as 10 amps per farad, or over 1 farad, which is equal to 10 volts per second. Once we get to the end of our 10 amp pulse, the current goes back down to 0, at which point the time rate of change of the capacitor voltage falls back to 0, because 0 amps over 1 farad is 0 slope. And next, when we apply the negative 10 amps, we're going to have a negative 10 volts per second slope. And this will decrease linearly until we end the minus 10 amp pulse, which will occur actually when the voltage gets back down to 0. Let's plot the power that is delivered to the capacitor. So the power will be 0 initially, because there is a 0 volt, 0 amp product. 0 volt times 0 amp. Then it will rise linearly, because we will have 10 amps times 10 volts per second. So we could write this as rising at 100 watts per second. It tops out at 100 watts. But as soon as it reaches 100 watts, our current goes to 0, and so we're back to a 0 VI product. So this drops down to 0, and now it's at 0 because it's, let's see, let me label this. I forgot to label our voltage here will be 10 volts during this time. So we'll have 10 volts times 0 amps. Now notice this here is the opposite of this one over here. You see, with the inductor, we had no voltage, but we could have current. With the capacitor, we can have voltage when we don't have current. And as we saw that energy was stored in the inductor by having current flowing, essentially creating a magnetic field, we now will see that energy is going to be stored in the capacitor by having a voltage, because the voltage is related to an electric field, which is where the energy is actually stored. Okay, let's continue. Now at time 2 seconds, we apply a negative 10 amp pulse. The negative 10 amp pulse times the positive 10 volts gives us minus 100 watts. And now we have a triangle that will work its way back to 0 watts. And yeah, so at the end we have a 0 volt times 0 amps. Okay. So we notice, like before, that in the case of the inductor, that the average power, okay, note average power delivered to cap is 0. However, we did store energy, and so we can draw this here. We'll say we have this current source, we have our capacitor, and initially, if we, my computer keeps acting up. Okay. So initially, when we apply, we have 0, well, let's say that if we have 0 amps, okay, but we have 10 volts across here, and this is a 1 farad cap, then we have actually, the question is, how much energy do we have stored? Well, we can do the same thing as we did previously with the inductor. We take this area, we're just going to have 100 joules per second times 10 amps, times 1 second times 1/2 equal to 50 joules. Okay, so we initially are going to deliver 50 joules okay, 50 joules from our current source, and then when we discharge, or we apply a negative current, okay, this will be negative 50 joules, and so we will be taking that 50 joules and we'll actually return it to the source. Okay, and the amount of energy that is stored is 1/2 C, the capacitance, times the voltage squared. Excuse me. Which in our case is 50 joules. So you have energy that is stored in the capacitor by way of a voltage across the terminals. And that is because the energy is stored in an electric field. And in the inductor, you have energy stored in the inductor when there is current flowing through it, and that is because the mechanism for storing energy in an inductor is a magnetic field. Now, in closing, I just want to point out an analogy, okay, analogy for both of these, mechanical analogies. Now we want to look at, in closing, some mechanical analogs to the capacitor and to the inductor. So we return to some first semester college physics or high school physics, where you studied the spring and the mass. And the law that's associated with the spring is the Hooke's law, which essentially describes the excuse me, the force that it takes to stretch a spring by some distance x of k here. So it says that the force, well, we'd say that the force exerted by the spring is equal to k times the extension or the displacement of the spring. Now this spring is analogous to a capacitor, and I want to show you how we can see that. So notice that the displacement x of k is actually equal to the integral of the velocity, right? Since velocity is equal to dx of k dt. Okay, and so we can write that f of k is equal to, and I'm going to define a new term here called ck, where ck is equal to 1 over k, and this is actually a real term. It's called the spring compliance, just like k is the spring stiffness. Okay, so the spring compliance, it's really like the spring's capacitance. If you look at this expression here, that is analogous to the voltage of the capacitor being equal to 1 over the capacitance times the integral of the current dt. Notice that the units of current are coulombs per second, and the units for velocity are meters per second. These are both what we call flows. They're flows because it's some quantity relative to time, right? Per unit time. Granted, meters per second is kind of abstract. You can't grab a meter, but it is nevertheless considered a flow. And f of k has units of newtons, and here we have volts. We can also rewrite volts as joules per second, and we can rewrite newtons as joules per meter, because recall, after all, if you apply a force 1 newton and you apply that force over a distance of 1 meter, you get 1 newton times 1 meter is 1 joule. So these are called what we call efforts. So, a larger force, bigger effort, right? Okay, if we were to plot, let's say if we were to apply a constant flow to our spring, okay, so constant flow would mean that we would have a velocity that was plus 10 and then minus 10, so this would be 10 meters per second, minus 10 meters per second. The spring would actually then undergo an effort, okay, that if we plotted the force, that would grow, right? That would grow to up to 10 newtons, and when the spring is no longer traveling, it's basically traveled for 1 second. Right, this is 0, 1, 2. It's traveled for 1 second at 10 meters per second, so it's traveled 10 meters. And let's assume, that we have a spring constant of 1, so it'd be 1 newton per meter. So our force will be 10 newtons, and it will stay at 10 newtons. And then as soon as we start having the spring travel at minus 10 meters per second, it'll go back to ultimately to its resting point, back to 0. Now, this looks a little unfamiliar because you normally would be thinking about the displacement, right? X of k. So if we look at x of k, what we actually have is x of k, we'll assume it starts at 0, and now it's going up to 10 meters, and it's going to stay at 10 meters, and then it's going to come back down to 0. And now we're back to, this is Hooke's law here, right? That shows that the displacement and the force are proportional. And you might say, well, where's the x of k for the capacitor? If I go back to the capacitor here, what I need to define, well, let me hold off on that. I'll come and do that at the end after we talk about the mass. Okay, so analogous to the inductor is the mass. So in general, the inductor and the mass are called elements of inertance, whereas the spring and the capacitor are compliant elements. Okay, so the mass and the inductor have like inertia to them. So here let's try to write an equivalent expression. We have that, we start with F equals ma, right? F applied to a mass will be equal to the mass times its acceleration. AM right here, A sub m. But A sub m is also equal to the time derivative of the velocity, so I'm going to write it that way. Now that is analogous. If you recall, we have the voltage of the inductor is equal to L d IL dt. So these are analogs. We can see that okay, the voltage is joules per coulomb. We have newtons per meter. And we have, for our flow, our current, we have coulombs per second. And for velocity here, we're going to have meters per second. So again, we have flow and we have effort. So if we were to apply, let's say, a constant force of 10 newtons and then minus 10 newtons. Okay, 10 newtons minus 10 newtons. And let's assume a mass of 1 kilogram. So now we would have a velocity that, just like the current, we had to make an assumption that the current has some initial condition. The velocity will say, we'll assume here that it starts off at 0. And when we apply a positive 10 newtons, then we have an acceleration that is going to be equal to 10 newtons over m. It's positive. So we'll have a slope of 10 newtons over 1 kilogram, which is going to be 10 meters per second, right? So this will go up to 10 meters a second, and then I shouldn't have these overlapping like this, but then it will go back down to 0. So this maximum velocity is going to be 10 meters per second. And you can work through both for the spring and the capacitor if you want to plot the power delivered to the spring, the power delivered to the mass, and now you're doing power as the product of velocity times force, right? Velocity times force is meters per second times newton, so that's joules per second, or watts. You'll find that you'll have those two inverted or opposite sign triangles where you're initially storing energy and then you're extracting energy. So maybe we can also plot the, let's see, if we plot the displacement here. Now I'm not going to, the displacement is going to be the integral of the velocity, which is going to be a square law, so I don't exactly want to try to plot that out. Anyway, those are the analogs. So if you're having a hard time with capacitor and inductor, understanding what they actually are doing, how they act as energy elements, storage elements, maybe thinking of the spring and the capacitor will help you. Lastly, very lastly here quickly, we talked about, for the spring, we had, we took Hooke's law, we wrote it this way, let's see, F is equal to, F of K is equal to K times X of K. I defined compliance, the spring compliance, so that I can rewrite this as 1 over the compliance of the spring, okay, times X of K. And now we can actually look at what is the definition of, how would we define the spring compliance, which is, 1 over the spring stiffness. We can say it is equal to, using that above expression, it's equal to X of K over F of K. In other words, it is some displacement meters per Newton. So if we say I have a 1 meter per Newton spring, it means that the spring's compliance is 1 meter per Newton, meaning that for every Newton that you apply, you'll get 1 meter of displacement. So what is the analog on the electrical side? So this is for the spring. But for the capacitor, we have the relationship that IC is equal to C dVc dt. Okay. And now if we were to, I'm kind of doing this backwards because normally this is derived from a more primal relationship that I'll arrive at in a moment. But here I'm going to, since I started out with this VI relationship, we'll work backwards. So if I multiply both sides by dt here, okay, these will cancel out. And now I can write C is equal to IC dt over dV. All right, now this is actually equal to, I is current, right, which is coulombs per second. Coulombs per second times dt, which is time, gets me charge. So I actually get d charge dVc, okay, which leads to the expression that capacitance is equal to charge. And I could say d-charge or delta charge, but just like here I didn't use deltas, I'll just say it's charge over voltage, okay, which has units of coulombs per volt. All right, so these are analogous. So when you think about the definition of a spring, of a capacitance for the capacitor, it's going to be coulomb. And pardon, this C here is not this C, right? This C here on the left is the capacitance. And on the right here it's the units of coulomb. So a 1 farad capacitor is a 1 coulomb per volt capacitor. That means that if you deliver 1 coulomb of charge to that capacitor, 1 volt will be developed. So 1 volt of effort, if you will be present across that capacitor. Just like a 1 meter per Newton spring would mean that if you deliver, we don't say deliver a meter, but if you displace the spring by 1 meter, just like we deliver a coulomb of charge to the capacitor, there will be built up 1 Newton of force or of effort. So the 1 Newton is analogous to the 1 volt. And that's representative of the energy that's stored. A spring only stores energy by having a force, not by having a velocity. All right, and a capacitor does not store energy by having a velocity, a charge velocity or current. It stores energy by having a voltage. Now, when there's a voltage, it does mean that there is charge, and when there is a force, it does mean that there is a displacement. So we have to be careful and not confuse, for instance, meters with meters per second, or displacement with velocity. The spring does not store energy by having a velocity. The spring will store energy by having a displacement, which is 1-to-1 tied to a force. Just like the capacitor doesn't store energy with a current or a velocity of charge, but it does store energy by depositing charge. So a net displacement of charge, if you will. Okay. All right, and then lastly, we can look at the inductor here. So we had, let's see, we had mass, and we have inductor. So we're going to look again at like the definition, if you will, of what is a mass, or what is an inductance. So let me just write them down because I'm running out of time. We have, with the mass, we have F is equal to ma, which I'm going to write as v dv dt. Now if we rearrange this, I can write the mass is equal to F times dt over dvm. This has units then of newtons seconds divided by meters per second. And what we have on the inductor side is we have VL is equal to L dIL dt, and we solve for L, and we say L then is equal to VL dt divided by dIL, and that leads to inductance being volts times seconds divided by coulombs per second, or amps. And I want to point out the analog between these two here, just like we had it, oops, right here. Okay, so this is a strange way to think of mass, okay, but we can define a mass. Of course, the units here, the mass end up being the kilogram, but it's just a different way of looking at it. If we say we have a 1 kilogram mass, it means that if you apply 1 Newton for 1 second, you will have accelerated that mass to a 1 meter per second velocity. So apply 1 Newton for 1 second, and at the end of that 1 second, your 1 kilogram mass will be traveling at a meter per second. And it will have an energy stored of 1/2 1 kilogram times 1 meter per second squared. So it'll have a half a joule. Same thing for the, or similar thing for the inductor. 1 Henry inductor says that if you apply 1 volt across that inductor for 1 second, so this is really saying if you apply a particular effort for an amount of time, you will get so much flow. That's what it was for the mass, it's what it is for the inductor. You apply 1 volt for 1 second, and at the end of that 1 second, you will have 1 coulomb per second of flow, or 1 amp. So I'll stop here and hope that this initial lesson is helpful in introducing the what's different about a capacitor and an inductor relative to a resistor, and then hopefully it's made it established a relationship, an analog between the electrical and mechanical domain. I'll say that traditionally when I've introduced inductors and capacitors, I've gone back to UFIS, where the capacitance was computed from 2 parallel plates, with a dielectric in between, and there's electric field, and there's the geometry there, and you arrive at a capacitance. I've done the same with the inductor. And so hopefully this approach, which is completely abstracted away from however physically or physicsy we actually arrive at a capacitor or an inductor, we've just looked at its terminal characteristics. And I think this perspective will be much more helpful as you go forward and you consider how capacitors and inductors behave in an electric circuit, which is really the focus of the course that we're in at present. So that's all for now.